Hello everyone, and welcome to chapter 7 of me learning Rust. Today we'll continue with the ownership chapter, I think chapter 4 in the book, and we'll learn about the slice type. So let's just jump in. Let's open VS Code, delete everything, print hello, see what we can run. Yep. Great. So, the slice type. Slices let you reference a continuous sequence of elements in a collection rather than the whole collection. A slice is a kind of reference, so it does not have ownership. Okay, so slice is a reference to part of a collection. Okay, here's a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word it finds in that string. If the function doesn't find a space in a string, the whole string must be one word, so the entire string should be returned. This is a common problem, especially with the parsing. I think one of the projects I would like to do at the end of this book is to write some sort of parser, maybe a JSON parser, or maybe a TOML parser. It's good practice for working with strings, with the tokens, and understanding file structure. Textual file structure. Okay, let's work through how we'd write the signature of this function without using slices to understand the problem that slices will solve. Okay, I think I know what slices are. It's like a part of the string, a reference to a part of the string, but I'll try to follow the book and see. Okay, so we have function, first word, that the first argument and the only argument is a reference to a string, and I have to return a substring or something. But here's the question mark. The first word function has a ref string as a parameter. We don't want ownership, so this is fine. But what would we return? We don't really have a way to talk about part of a string. That's where slices will come in, probably. However, we could return the index of the end of the word, indicated by a space. Let's try that, as shown in listing 4.7. So I guess if it's like I32, I use size. Okay, you have to learn that use size is the return type for anything that's related to indexing. Okay, so let bytes equal s bytes. Yeah, I guess character is different than a byte, so, but I don't understand why. But whatever. Then we do a for loop of a tuple I and the reference to an item, n bytes iter enumerate. Okay, and then I open this, and if item is equal to the byte space, then I return I, and else I return the length of the string. Okay, so before we continue reading, I'll try to understand what I'm seeing here, because there are some new stuff here. First of all, and this is the last thing I'll check before I continue, is why I'm turning this into bytes. Like, why can't I use the characters that are part of the string? This is question number 1, and question number 2 is we're seeing this. So I want to see first, like if I do bytes iter, what is the type of the iterator? It's iterator over u2. Okay, so probably iterator over u2 allows me to iterate, do a for loop over these characters of unsigned bytes, and if I do enumerate, it'd probably be an enumeration iterator. Okay, so I don't understand this syntax, but I assume that the enumerate, if I do an enumerate to an iterator, I get a reference to an item, and the index of the item. So the I is the index of the item, and this one is a reference to the item at location I. Okay, so I think we'll learn about this later because I saw a lot of keywords I'm not familiar with. But first I want to try to do it as a string and not as bytes. So if I do this and I iterate, like, is there an iterator for a string? Iterate. Or can I do for C in S? Will this work? Ooh. Yeah, I think it's more convoluted than bytes. Well, I guess that... I hope that the string chapter is a long one because I have a lot of questions about strings here. So let's revert back to this. This is the bytes. Okay, and this should work. Let's just run this function on this first word. And the answer should be 0, 1, 2, 3, 4, 5. Should be 5. Ah, it doesn't like it. Because this is not a reference, but if I do this, will this work? Nope. So I'm doing let s tr equals this. Oh, wait. This is a literal. So if I do string from, will this work? Wait. Okay, I need another space here. Will this work? Yep, it works. So I'm taking the string literal, I'm turning it into a string, and then I'm referencing the string. So I'm expecting to get a 6 here, or a 5. I think 6. Oh, 5. So it's 0, 1, 2, 3, 4, 5. Yeah, the 6th character is 5. Okay, great. So it works. This works. So let's read about it. Because we need to go through the string element by element and check whatever value is a space, we'll convert our string into an array of bytes using the sbytes methods. Next, we create the iterator. So they don't explain why they're doing this and why can't I iterate over elements of a string without converting it into bytes. Next, we create an iterator over the array of bytes using the iter method. We'll discuss iterators in more detail in chapter 13. For now, know that iter is a method that returns each element in a collection and that enumerate wraps the results of iter and returns each element as part of a tuple instead. The first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. Yeah. This is a bit more convenient than calculating the index ourselves. Yeah, this is fairly common practice. Okay. Because the enumerate method returns a tuple, we can use the patterns to destructure that tuple. Yeah, we'll be discussing patterns more in chapter 6. In the for loop, we specify a pattern that has I for the index in the tuple and the ref item for the single byte in the tuple. Because we get a reference to the element from enumerate, we use the ampersand in the pattern. Okay. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. Yeah, it's this B. If we find a space, we return the position. Otherwise, we return the length of the string by using slang. Yeah, so if we can't find any spaces, we go to the end of we just return the length of the string because this is one word as defined by this problem. We now have a way to find out the index of the end of the first word in the string, but there's a problem. We're returning a use size on its own, but it's only a meaningful number in the context of the string. Of this string. Like, In other words, because it's separate value from the string, there is no guarantee that it will still be valid in the future. Yeah, if we change the string somehow, if it was like mutable string, because although this doesn't get a mutable thing, but if you want to use it on a different string, maybe we did some operations, some shadowing, and I don't know. So yeah, when I'm getting a number without the string, it can be non-relevant when I use it. Okay. In other words, because it's a separate value from the string, there is no guarantee that it will be valid in the future. Consider program listing for 8 that uses the first word function from listing for 7. So we have a mutable string. Let's just use this one. So we create a mutable. We create a mutable string. We word equals first word, and we get with a reference to s, and then we do s clear, which I guess makes the string null. Why doesn't it like this? Oh, okay, I think now it will be okay. Yeah, and now I want to. The word still has value 5 here, but there is no more string that we could meaningfully use the value 5 with. The word is now totally invalid. Yeah, so there's no need to run this. Yeah, but okay, let's just do this to get rid of the warning. Okay, let's read on. So basically, if you like, I understand that I get this mutable string. That means I can change its content. I pass it on as non-mutable because the first function will not change it. It can treat it as non-mutable. I get the location of the space of this space, and then I change the string. So from line 15, this word variable is no longer valid. Okay. This program compiles without any errors and would also do so if we used word after calling sClear, because word isn't connected to the state of s at all. Word is still contain the value 5. We could use that value 5 with the variable s to try to extract the first word out, but this would be a bug because the content of s have changed since we saved 5 in word. Okay, having to worry about the index in word getting out of sync with the data in s is tedious and error prone. Managing these indices is even more brittle if we write a second word function. Its signature would have to look like this. Okay, yeah, so beginning and end probably. So this will be the beginning and this will be the end. This is basically what I use when I write tokenizers in C. I have this, just side note, I have this structure when I have character to the entire data, a link, a pointer, not always, and I have something like size t start and size t length of the token. So anytime I can go in and just have the word, and my tokenizer just has a big structure, a big tree of these kind of objects. But I'm speaking too soon. I think when we will do the projects after all the chapters here, I'll talk about this, because now I'm starting to think that JSON tokenizer is a really good project to write. Okay, let's continue. Now we're tracking a starting and an ending index, and we have even more values that were calculated from the data in a particular state but aren't tied to the state at all. We have 3 unrelated variables floating around that need to be kept in sync. Yeah, it's the string and start and end. I prefer not to use end, prefer to use length, because it's easier to do calculations, like one less operation, and it's very easy to debug this because I use length more than the end. Yeah, the only downside of it is with end it's easier to check overflows, but if you parse correctly, you can do this check at parse time and you don't have to worry about this value in the future. Okay, luckily Rust has a solution to this problem: string slices. Okay, a string slice is a reference to a part of a string and it looks like this. Okay, so we have a string and we have a hello, it's a reference, and this is probably the slice. So it's like first word and the second word probably. Hello and world, right? So it's basically like Python syntax, the most familiar with. Rather than a reference to the entire string, hello is a reference to a portion of the string, specified in the extra 0 to 5 bit. We create slices using a range within brackets by specifying starting index and ending index, where starting index is the first position in the slice and ending index is one more than the last position. Just like Python, just like any indexing of arrays that's in most of the programming language, except some unusual languages like Fortran. Okay. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index minus starting index. Okay, so internally it stores the length. Okay, yeah, I also prefer this. It's good. So in the case of let word equals 6 to 11, world would be a slice that contains a pointer to the byte at index 6 of S within a length of 5. Okay. I would assume that this structure allows to keep track of the string at compile time, so that if I change something, the slice would be notified by the compiler that the original string would change, and then we'll get an error. This is what I'm expecting. We'll see if it's true. So we have this. We have the string, which has a pointer to the entire data, length and capacity, and a world, which has a pointer and a length. Yeah, I keep always the pointer to the beginning, but I don't know what's the reason. It's just how I write this. Okay, with Rust's double point range syntax, if you want to start at index 0, you can drop the value before the 2 periods. Okay, like this. Great. By the same token, if your slice includes the last byte of the string, you can drop the trailing number like this. Okay, that means these are equal. Okay, you can also drop both values to take a slice of the entire string. Yeah, I think I'll try to rewrite this thing instead. Like, before looking forward, I'll just read this note, and then I'll try to rewrite the function as I think it should be, and we'll see if that's what they suggest. So note, string slice range indices must occur at valid UTF character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For the purpose of introducing string slices, we're assuming ASCII only in this section. A more thorough discussion of UTF-8 handling in the storing UTF encoded text with strings section of chapter 8. Okay, so I'm assuming it's this ASCII. So let's write function, let's call it my first word. Yeah, and I'm getting a string, and I'm returning a slice. Just before that, I want to see how I define slice. So let's see, let slice equals S3. Let's see. It's just a ref to a string. Okay, and I return a ref to a string here. I'll copy this. Here I return the full string as a reference, and here I return I, like this. Okay, that looks like it's compiles at least. So let's go forward and try to see if M was correct. With all the information in mind, let's rewrite first word to return a slice. the type that signifies string slice is written as str, and everything looks pretty much the same as I wrote. Excellent. That means I understand a little bit about the slices and about reference and how it works. It makes me happy. Okay, we get the index for the end of the word the same way we did in listing 7.4 by looking for the first occurrence of a space. Yeah. When we find the space, we return a string slice using the start of the string, and the index of the space is the starting and ending indices. Yeah. Now we call first word. When we call first word, we get back a single value that is tied to the underlying data. Value is made up of a reference of a starting point and the slice and the number of the element in the slice. Okay, returning a slice would also work for a second word function. Yeah, so we can write second word function if we want. Okay, maybe at the end of the episode I'll write a second word. We'll see if it works. Okay, now we have a straightforward API that's much harder to mess up because the compiler will ensure the reference into the string remain valid. Exactly. Yeah, that's I think that's the takeaway from this, that using the slice instead of just structure or variables to keep track allows the compiler to do the tracking for us during compile time and throw an error if we're misusing or changing the string after we've created the slice. Okay, so remember the bug in program listing 4.8, and this is the bug. Yeah, when we got to the index at the end of the first word, but then cleared the string, so our index was invalid. The code was logically incorrect, but didn't show any immediate errors. So wait, first of all, I change it to my first word, and this becomes a string. And now, when I try to change it, it says that cannot borrow s as immutable because it's also borrowed as immutable. Mutable borrow occurs here. Okay. This is not very clear, this error. It's also the error that we see here. But let's see how they explain this. Like, I know why it happens, but the error is not very informative. The problems would show up later if we keep trying to use the first word index with an emptied string. Slices make this bug impossible and let us know we have a problem with our code much sooner. Using the slice version of first word will throw a compile time error. This is the compile time error. Let's read it again. Cannot borrow s as immutable right here. Okay. Because it is also borrowed as immutable here. Like it borrows as immutable. Okay. And I understand here in the first example, we borrowed it and then we return. Like the scope is exited. But here we're borrowing it again. Like we borrow and borrow again when we return the value. So the borrowed value resides here. Yeah. Okay. And I'm using it later. I wonder what happens if I'm doing this. Okay, now it's not an error because I'm not using it later. So what it says is I'm borrowing it here. I'm using it as an immutable later, but here I'm trying to borrow it as a mutable. And if I switch this, I'll also not expect it to get an error. Yep. Okay, this is very, very helpful. This will help with so much bugs. Recall from the borrowing rules that we have an immutable reference to something. We cannot also take an immutable reference because clear needs to truncate the string. It needs to get a mutable reference. The print line after the call to clear uses a reference in word, so the immutable reference must still be active at that point. Rust This allows the mutable reference in clear and the immutable reference in word from existing at the same time, and compilation fails. Not only has Rust made our API easier to use, but it also eliminated an entire class of errors at compile time. Yeah, this is really good. I like it. I like it. String literals as slices. Recall that we talked about string literals being stored inside the binary. Now we know about slices, we can properly understand string literals. So we have the string literal hello world in S. The type of S here is ref string. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable. String is an immutable reference. So we encoded slices right at the beginning, right? The first line of code that we ran had a slice. It's a slice of memory in the binary, of part of the binary that contains the string hello world. Okay. String slices as parameters. Knowing that you can take slices of literals and string values lead us to one more improvement on first word, and that is its signature. This is the original signature, and more experienced Rustation would write the signature shown in listing 4.9 instead because it allowed to use the same function on both string values and like both string references and string slices. So if I'm changing this to regular str and also here, that allows us to, yeah, it doesn't change anything except here, mutable. Okay, let's just use this. Everything looks okay, and I can use, I think now I can do this even. Or even this. Yep, now I can do this because this is a ref string, like a slice, a string slice. Sorry, I'll need to practice on that. So now I can shorten this code. Okay. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or reference to that string. This flexibility takes advantage of deref coercions. A feature we'll cover in implicit deref coercions with functions and methods. Section of chapter 15. Okay. I don't know what they mean. Implicit deref coercions. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing functionality. Yeah, so we can use slice here. We can use the entire string. We can use reference to the string. We can use a literal. We can use like a slice of a literal, then slice of the entire literal and the literal in itself. Okay, other slices. I think let's finish this and then I'll write the borrow nth word or something. String slices are as you might imagine, are specific to strings, but there are more general slices types too. Consider this array. Yeah, we have this array. Just as we might want to refer to a part of a string, we might want to refer to a part of an array. We do so like this. This is the slice. This is probably assert equal. Okay. The slice has the type ref of I32. It works the same way as a string slice do by storing a reference to the first element and the length. You'll use this kind of slice for all sorts of other collection. We'll discuss this collection in detail when we talk about vectors in chapter 8. So I guess there's like a class of objects called collections that can be sliced in Rust. This is, I don't know if this statement is 100% correct, but I'm going with this until something in the book indicates otherwise. Okay, summary. The concepts of ownership, borrowing, and slices ensures memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage in the same way as other system programming languages. But having the owner of data automatically clean up the data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further throughout the rest of the book. Let's move on to chapter 5 and look at grouping pieces of data together in a struct. Okay, so before we go to chapter 5, I just want to write a function called nth word. Yeah, I want to get a string, which is a slice of a string, and U32, which indicates the number of the word I want. I return slice. Forgot the colon. Yeah. Sorry. Like this. And now, I wonder if there's like empty result. But I say if we can't find anything, we'll return an empty string. Will this work? Okay, so we'll return an empty ref, or will this work? No. So we return an empty slice, and let's first of all convert this string into bytes. We make a mutable counter to count the word that we're on. Call it current word, and we initialize it to 0. Now we add the 0th word, and then we do this for loop I. Yeah, we'll add another variable later. Item in bytes iter enumerate, and here if item, we finished the word. If this happens, then we want to see if the current word is equal to n. If this is the word that we're looking for, then we want to return a slice of the string. But now we don't have the beginning of this slice. We know that the end is I, but we need to have the ending. So we have a mutable. It's going to be usize, I think, automatically, but previous word end, which is 0 by default, and I'm going to put it here. And it's going to be, I need to do a return here, right? And an ampersand. Okay, and if I find the word and it's not the nth word, I don't think I need an else here. I can do previous word end equals I plus 1, because we're in space here. Okay, so I have this. This will find the nth word. The problem that we could have is that I is the last index here, and this might create overflow, but not really, because if I is really the last index and I'm getting here, then nothing will happen. Like if the last character is a space, then nothing will happen. So this should work. So let's try this. Nth word. Let's delete this. And we have, sorry, a string literal will do 1, 2, 3, 4, and 5. And let's do it, call it S. And I want to get the third word here. I have some warnings. Current word, of course. Yeah, I forgot to add 1 to the current word. Also, if I'm getting a space, then it's the next word already. So now let's run, and we get 4, which is in index 3. And if we want to be index 0 is 1, I think we'll leave it like this. So here I'm getting the nth word using what we learned here. I guess you can do it better. And maybe after chapter, chapter about strings, we'll write something that's better here. Thank you very much. See you next time.